Hello everyone. So this is the very first video of the series of videos that I'm gonna make about DC biasing. DC biasing. Before going into the details of DC biasing, we should know that we are gonna study about BJTs. So what are BJTs? BJTs are bipolar junction transistors, and there is a common feeling about BJTs that BJTs are somehow magical device that somehow raise the level of input AC in the output. They provide a raised output AC level, and people think that they do it magically, but it is not the fact. Be there are DC supplies associated with the working of a BJT as an amplifier, and these DC supplies provide the energy to raise the output level of the AC supply. So there's two part associated with the study of this, that is the AC part and the DC part, and here the superposition comes to our rescue, so we can study them separately. And in this series of videos we are going to study about the DC supplies only. So now, what is biasing? Biasing is the process of application of DC voltages to fix the level of current and the voltages, and when we fix the level of the current and the voltages, we get a fixed point in the output characteristic, and this fixed point is called the Q point. So to fix the level of this Q point, we need biasing. Okay, so what is the need of biasing? To fix the Q point or the operating point. Now, uh, before going into the detail, I think there is something that everybody should know, and that is, these are the important formulas that you should know before going into the further lectures or videos. So VBE, this is the voltage across base and emitter junction. First of all, we all know that a transistor is composed of two PN junctions. One is base and emitter, and second is collector and base. So when the base and emitter junction forward bias and collector base junction is also forward bias, then they operate in the saturation mode. Then the BJT device operation in the saturation mode, and the application can be as an on switch. You can have a look here. See, this region is the region when the BJT will operate in the saturation mode, and as you can see, this line is approximately VC is equal to 0.3 volt. So when VCE is less than 0.3 volt, then we can say that the device is in the saturation mode, and when IB is less than 0 microampere, then this is the cutoff region, and this region over here is called the active region or the linear region. Why do we call it a linear region? Because as you can see, these spaces are equal. The separation between the two successive IB curves is same, so we can say that BJT acts as a linear device in this region. And in the saturation region, when you draw a DC load line over here, then you can see that the current is on the higher side, and in the cutoff region you can see that the current is on the lower side. So in the cutoff region, ideally there is no current, and in the saturation region the current is very high. Okay, and our area of interest is this region, region, where the BJT works as an amplifier. In the active region, the emitter base junction is forward bias and the collector base junction is reverse bias, and we do not use BJTs in the attenuators normally, because simple RC circuits can act as an attenuator, so there is no need of an active device like BJT to act as an attenuator. Now we have to fix the operating point. Then the question arises that where to fix it. So there are 4 points over here. As you can see, if we take the operating point here near A, then it can go in the cutoff region, so this will not give us the faithful amplification. And again, if we use it here, if we fix it here near B, then it can go in the saturation region. so there cannot be a much voltage swing here associated here. And this line here, this is called the maximum power dissipation curve, and this maximum power dissipation curve, this somehow decides the uh, mm, life of the device. Okay, so if we operate here, then we are operating beyond the maximum power dissipation, beyond the maximum power rating of the device, so there are chances that the life of the device can be diminished or the device will get corrupt. So we mostly use it here in the center, so this allows the maximum voltage swing, and this will give a faithful amplification, so we use it here normally. And lastly, you need to have a look at these formulas here. These will be used in detail. See, VB is equal to 0.7 volt in Si, and it is 1.2 volt in gallium arsenide semiconductors and 0.4 volt in germanium conductors. And IE is equal to beta plus 1 IB, and IC is equal to beta IB. So since the beta value is generally very large, 50 to 200, so we can approximate it as IC. This approximation will be used mostly in our discussion, so we must know these. And this IC equation can be more specifically written as IC is equal to beta IB plus beta plus 1 ICO. Now, DC biasing configurations. There can be DC many configurations, like the fixed bias configurations, emitter follower configurations, and others. But see, we called the operating point as the Q point. Q point means quiet point or the still point. So this point should not move ideally. This point should stay where it is, but theoretically Q point changes. And how will it change? A Q point is defined by, on the two axes, by IC and VCE. So when VCE changes, Q point will change, and when IC changes, then also Q point will change. And when will IC change? IC is equal to beta IB plus 1 plus beta ICO. So when ICO will change, IC will change, and in turn this Q point will change. And if beta will change, then again IC will change, and then again the Q point will change. And another thing is VBE. Sometimes VBE also changes, and when VBE changes, then IB changes, and in turn IC changes. So we are gonna study about all these in the next series. Do watch the next series if you want to know more about DC biasing. Thank you.